Okay, so in this video, we will consider another example of eigenvalues and eigenvectors. And the topic will be recursive sequences. Now this term should sound familiar, right? In integral calculus, you actually studied sequences. And all a sequence is an infinite list of real numbers. In integral calculus, on the other hand, you are always given a sequence with an actual explicit formula for every given term of the sequence. But not every sequence is actually given this way. So in here we'll consider special types of sequences called recursive sequences. And what a recursion is a way to get the next terms of the sequence from the previous terms. And here we'll consider only one type of recursive sequences. We'll consider so-called second order recursive sequences. And you'll see why we use the word second order in a second. Consider the following example. Suppose we said we'll have a sequence. So x0 is the first value of our sequence, then x1, then x2, and so forth. And here's the recursion. We're given two initial values. So we're going to take the values for x1 and x2, x0 and x1, sorry. Suppose that x0 is equal to 1 and x1 is equal to 2. So all we're given are the first two values of this sequence. And then this third part will be the recursion. How do we get the n plus 2th term from the previous two terms? So the next term will be 5 times the previous term, so x n plus 1, plus, say, 14 times the term before that one, xn. And this will be the recursion for n greater than or equal to 0. So let's see now with this recursion how we can build the sequence one term at a time. How we can find x2, then x3, then x4, and so on. So what if I wanted to find the next term, x2? We already have x0 is 1, x1 is 2, and again, these you choose any given values of your choice for the first two values. And you see the second order is because you have that the next term will be dependent on the previous term and the term before that one. So if you want to find x2, well, that means n has to be 0. So set in the recursion n equals 0. And the implication is, well, x2 will be equal to 5x1 plus 14x0. But we know x1. x1 is simply 1. 5 times 1 is 5. Plus 14 times x0. Whoops. My bad. 5 times x1. x1 is 2. So 5 times 2 is 10. Plus 14 times x0. x0 is 1. 14 times 1 is 14. And so x2 is 24. So we can write the sequence here if you want. x0 was 1. x1 was 2. And now, from the recursion, x2 equals 24. So we now have the third term of our sequence. What if we want the next one? Well, that would be x3. If you want x3, pick n equals 1. And then x3 equals to 5x2 plus 14x1. Well, we have just found x2. It's 5 times 24. 5 times 24, well, 5 times 20 is 100. 5 times 4 is 20, so that's 120. Plus 14 times x1, x1 is 2. 14 times 2 is 28. And what you have is now 148. And that is x3. the fourth term of your sequence. And you can keep going like this, building the sequence one term at a time. If you want the next term, well, choose n equals 2, and you'll have x4, and then you keep going like this. The only problem with this is, what if I ask you to find the 1000th term of the sequence? You see, you can't just jump straight to the 1000th term. You need every term before that one. You see, you could not find x3 without knowing x2 and x1. And you will not be able to find x4 without knowing x3 and x2. So if you want the 1000th term of the sequence, you have to build every term leading up to the 1000th term. The question we're going to ask is, can we find a shortcut? Can we find a formula for xn for any n? So could we find the 1000th term of our sequence without finding any of the previous terms? And the answer actually is yes. And the solution lies in eigenvectors and eigenvalues. We will try and rewrite the system as a matrix equality, right? The recursion drives the sequence forward. It tells you to build the next term, do 5 times the previous term plus 14 times the terms before that. So this recursion drives the sequence. It allows you to build each term consecutively. The question is, can we drive the sequence with a matrix? So here's my question. We will ask, suppose we write as a vector the vector xn plus 1, and can we find a 2 by 2 matrix, which we'll call A, so that if we multiply the vector xn plus 1 by the matrix A, the sequence will move forward by one step. So xn will become xn plus 1, and xn plus 1 will become xn plus 2. So we really here are simply asking a question. Can we drive the sequence forward by one step using a matrix multiplication? Let's look up, right? The first term is xn plus 1. Well, you already have here xn plus 1, so do 0 times xn. So 0 times xn plus 1 times xn plus 1, and you will obviously have xn plus 1. And now you see the next term is xn plus 2. So you have to build xn plus 2 from xn and xn plus 1. But look at the recursion. Xn plus 2 is 5 times xn plus 1 plus 14 times xn. So if you check this out, you'll have the second entry is 14xn, check, plus 5xn plus 1, and we know 14xn plus 5xn plus 1 is equal to xn plus 2. Mission accomplished. So we are able indeed to drive the sequence forward, no longer from the recursion, but with matrix multiplication. Well, if we want to build a sequence, we have to start with a vector that we actually know the values of. Well, that's the vector x0, x1, the initial vector of values, or the vector, sorry, of initial values. So now think of it. You have this matrix A. So if you multiply the vector x0, x1, and this vector you know is the vector 1, 2, by the matrix A, you know the matrix A drives the sequence forward by one step. So this vector will become the vector x1, x2. Well, what if you multiply by A again? What if you do A squared times the initial vector x0, x1? Well, all I did is I multiplied this side by A to get from A to A squared. Well, multiply this side by A again. You have A times x1, x2. But we already have checked that the multiplication of a vector by A drives the sequence forward by one unit. by one step. So a times the vector x1, x2 will give you the vector now x2, x3. And you can see where this is going. Let's do one more step. Let's multiply now all of this by a. We'll have a cubed times the initial vector x0, x1 will be a times this vector, multiply this by a, this by a. But we know multiplying a vector of this type by a drives the sequence forward by one step. So the vector x2, x3 will become the vector x3, x4. And you can see now where this is going. If you wanted to build the nth term of the sequence, take the initial vector values x0, x1, which we know is equal to, if you just go back, we know this vector. It is the vector 1, 2. And if you want to drive the sequence forward by n units, you see if you multiply this by a 3 times, you move the sequence forward by 3 steps, so x0 becomes x3 plus 3, x1 becomes x4 plus 3 again. So if you multiply the initial vector values by a n times, every time you multiply by a, you move the sequence forward by one step. So if you multiply the sequence by the vectors here by a n times, you will move the sequence forward by n steps. So x0 will become xn, and x1 will become xn plus 1. So you know this vector, it's 1, 2. You know the matrix A, 0, 1, 14, 5. And you see, if you want the formula, that's what we'll call a closed form for the sequence. It's just a formula for the nth term. If you want the formula for xn, all you need is a formula for the nth power of a. But this is something we've done in the previous video. So I will let you check out that indeed, if you find the nth power of this matrix, you will find the following answer. So a to the n, the matrix A was simply 0, 1, 14, 5 to the nth power, sorry. And again, you know from the previous video that you can find the formula for the nth power of a 2 by 2 matrix using your knowledge of eigenvalues and eigenvectors. And if you do so, let me check it. You should get the matrix 1 over 9 times 2 times 7 to the n plus 7 times negative 2 to the n. Then you should have 2 times 7 to the n plus 1 plus 7 times negative 2 to the n plus 1. This is your first column. For the second column, you should get 7 to the n minus negative 2 to the n, and then 7 to the n plus 1 minus negative 2 to the n plus 1. And again, this is just using our knowledge of eigenvalues and eigenvectors. So now we have a formula for a to the n, so we can now get the formula for xn, right? If you remember the previous equality that we had derived, the vector xn, xn plus 1 is simply the matrix a to the n times the vector of initial values 1, 2. So let's rewrite that on the second page. So the vector xn, xn plus 1, is just a to the n. Well, there it is. So let's rewrite it. So a to the n, 1 over 9, 2 times 7 to the n, plus 7 times negative 2 to the n, 2 times 7 to the n plus 1, plus 7 times negative 2 to the n plus 1. Second column, 7 to the n minus negative 2 to the n, and then the other entry is 7 to the n plus 1, negative 2 to the n plus 1. So this is a to the n times, right, if you just go back one more time, xn xn plus 1 is a to the n, this is a to the n right here, times the vector of initial values, which was for us 1, 2. So times the vector 1, 2. And here, you don't have to multiply the whole thing, because all you care about is the xn value. So all you have to do is do the first row times the column, and you will get the value of xn. And you will have now a formula for the nth term of the sequence as a function of n, independently of the previous terms of the sequence. So let's compute this. We have 1 over 9. The 1 over 9 multiplies everything. So it'll be 1 over 9 times, well, the first entry, this, times 1. So it's just this. So 2 times 7 to the n, plus 7 times negative 2 to the n, then plus, right, this entry times this one, plus this entry times this one. So plus 2 times this entry. So we have plus 2 times 7 to the n, minus 2 times negative 2 to the n. And this is now the nth term of your sequence for any n. Of course, we can simplify this a little bit. What are we going to get? So xn is, well, 2 times 7 to the n plus 2 times 7 to the n. That's 4 times 7 to the n. Then what do we have? Well, there's 7 times negative 2 to the n minus 2 times negative 2 to the n. Well, 7 minus 2 is 5, so plus 5 times negative 2 to the n. And don't forget, all over 9. And this is true for any given n starting at 0. And you see, you no longer need the recurrence to find the terms of your sequence. You have a formula now. For any given term of your sequence, if you want the nth term, plug n in here, and you'll have the term. Well, let's check this out. Let's go back to our sequence. We had found that x0 was 1, x1 was 2, x2 was 24, x3 was 148. Let's just check that our formula holds for x0, x1, and x2. So we had found that x0 was equal to 1, x1 was equal to 2, and x2 we found to be 24. So let's just check that this formula holds, that we haven't made a mistake in our calculation. So x0, if we use the formula, well, 4 times 7 to the 0 is, this is 1, so it's just 4, plus negative 2 to the 0 is 1, plus 5, over 9. 4 plus 5 is 9 over 9, which indeed gives us 1, as expected. Let's compute now x1 from the formula. So we replace n by 1. So we have 4 times 7, that's 28, plus 5 times negative 2, so negative 10, over 9. But that's just 18 over 9, which is positive 2. As expected, check. And let's compute finally x2. Well, x2, again from the formula, replacing n by 2, you'll have 4. 7 squared is 49, plus 5 times negative 2 squared. Well, negative 2 squared is 4. 4 times 4 is 20. So that's plus 20 over 9. Well, 4 times 4 is 16, so it's 160. 160 plus 4 times 9, 36, plus 20. over 9? Well, what do we have? We have 160 plus 20, that's 180 over 9, right? So I combine these two together, plus 36 over 9. But 180, if you think of it, 18 over 9 is 2, times 10 is 20. So that's just 20, plus 36 over 9 is 4, 20 plus 4, and would you look at that? As expected, x2 is 24. So now, if I said what is the thousandth term of the sequence, you no longer have to do, okay, I'll find x3, then I'll find x4, x5, up to the thousandth term. All you got to do is say, well, x 1,000 would simply be 4 times 7 to 1,000 plus 5 times negative 2 to 1,000 all over 9. This would be a huge term, right? This would be a really, really big number, but you didn't have to compute any of the previous 1,000 terms. You can find any given term of your sequence just by replacing it by the appropriate value of n. And that's what we call a closed form of the sequence. All it means is you have found a formula for the nth term of your sequence that only depends on n and not on the previous terms. So one more reason to like eigenvalues and eigenvectors.